Welcome! In this series of short videos, we will look at topics common to both the PowerBasic console and Windows compilers. Today, we will look at compile options. PowerBasic as a language has been around for about 30 years. BASIC as a language has been around very much longer. So over this time, the language has evolved. And as such, there have been many changes to the syntax. What we're going to look at first of all are variables. As you've seen in the previous videos, we've declared variables like so. We can declare them locally within a subroutine or function, or we can declare them globally. But we always give them a name, and we always say what type the variable is. Traditionally, what you could do in basic dialects is define your variables slightly differently. If you used a command such as this, a def-lng, which is define all the variables between a and d as being longs, it would mean you could actually use your variable without declaring it inside the function. Now, if we turn off our dim all compile time option at the beginning, and we try and compile that now, it would compile quite successfully. The variable a has already been dimensioned as a long variable. These commands still exist within PowerBasic, but they're mostly for support of legacy code. Generally, it's not recommended that you use this method of declaring your variables for one simple reason. While the variable has been declared as being called a, you have absolutely no idea what a is going to be used for. In many cases, we declare variables to be used as simple counters, but in other cases, they are pointers to objects within our code. Say, for example, we wanted to do this. We're using a as a counter between 1 and 7. Now, that's fair enough, but if we actually change it to say this, the code becomes a little more self-documenting because the name we've given the variable is day, therefore counting days between 1 and 7. So naming your variables sensibly is a really good idea. So if we take this command out and attempt to compile our program, it will complain that we have quite correctly not declared the variable a. Traditionally, you could get away with this by adding a suffix to the end of the variable name which indicated what kind of variable it was. In this case, the percentage was the definition of an integer. If we compiled that now, it would compile quite successfully. Now, while this will still work within PowerBasic, its use is more or less deprecated now. It's a really good idea to use the dim all at the beginning of your code as one of your compile time options. With dim all in place, the program will error when you try and compile unless a variable has been declared. So if we run that now, it would say we're missing a declaration for the a variable, even though it's followed by a percentage sign. If you locally declared it as so, this would compile. Another thing to watch out for in your variables is whether a variable is either global or local. Now, we have declared a local variable here called string a. If we went up to the top of our code and put this in place, we are declaring string a as a global variable, and it's also declared as a local variable. If we try to compile that now, it would compile quite happily. However, you can see the confusion that this would actually give us if at some point in the code we had actually set the value of string a. So if we have a subroutine, we have declared the global at the top of the code. Therefore, in our pb main function, we're setting the value of that global. Now, we've redeclared the STRA as a local variable within the funProcess function. So if we attempt to actually put that value out to our log, and then we call our function in here, and we run our program now, we'd see the value that went out to the log was in fact nothing, an empty lint string. So despite the fact we set the value of this global variable to the word test, when we call our subroutine, in the subroutine we've declared a local variable of the same name. And while this doesn't change the value in the global variable, it means any reference to this string within our local function will output the local value. Now there are two ways around this. Generally I declare my global variables with a G in front of them. That way in the code it becomes really obvious that I'm setting the value of a global variable because it's preceded with a letter G. Now this effectively changes the name of the variable, so it's obvious to myself and also to the compiler that these are two entirely different variables. However, another thing you can actually do in your code is you can actually use a compile time directive to make sure that all your variables are uniquely named. Unique var on will do that for you. The default is unique var off, but if you put unique var on, if we attempted to actually do this, we'll put our global variable back to the same name. Now while this compiled before successfully, this will not now compile because the variable name must be unique. So it's quite handy to have that, because if you have global variables called one thing and you're declaring a local of the same name, there can be confusion in code, especially if you're not the one who actually wrote the code, or if the global variables are defined within some library. For example, the common display library may have global variables in it, and if you declare a local variable of the same name with the unique var on, it will fail at compile time and remind you of the fact you're using a variable which has already been declared, saving any confusion. Now, one thing to point out, if you've actually got that, let's take that off for a moment, and let's declare a global variable which is an array. So we've declared a global. So we've declared a global array that is a string, and I'm calling it data. And at the stage of actually declaring it, we're not actually saying how many dimensions this array actually has. We're just making sure that we have the name set up and the type of the array. Now within our code we can then redimension that array to be the correct size. Now if we try compiling that now, it will compile quite cleanly. We have redimmed the array for 100 elements as a string, which was exactly the same as it was initially set up. However, the way PowerBasic actually works, if you're doing a redim, you could make a mistake in typing and type this in as a long. Now this would still compile, but the array which you considered to be a string array, you wanted it to be 100 elements, but you've now redimmed it as a long. Now this will cause some confusion because when you try and put values into that array, you may think you're putting it into a string array. And as soon as you try and do that, the compile will fail because you're trying to put a string into an array which is effectively numbers. How you can get around that, if you leave the unique var on, if we compile that now, it will effectively error because it's saying the array name must be unique. It thinks you're trying to recreate a variable array as a different type. So this will pick up this particular error. Now it will also do it if you put it as string. What you need to do in this case is, since you've already declared it as a string, you don't have to tell the program again it's a string, you merely have to tell it how many dimensions it's going to have, and it will remain as a string. So this is a good one to have in your code because it will quite happily pick up these kind of typos. Now, there are other options which exist in the help file it's worth having a quick look at. Probably the most popular one is the one right at the very top, the option for large memory 32. One of the constraints of a 32-bit Windows application, which PowerBasic is that you are limited to how much memory you can actually use on the computer. Now generally this is about 2 GB of memory. I must be honest, in the many programs I've actually written, I've never needed a program to have access to more than 2 GB of memory, but I suppose if you're writing some programs with very large datasets, it may be possible you wish more than 2 GB. Now, when the Windows operating system was a 32-bit operating system, this was pretty fixed. However, with the move to 64-bit operating systems, we now have a lot more memory space available. On many computers, 8 GB of memory is considered the minimum. And it's quite common now to see computers with 16 GB, 32 GB, and even 64 GB of memory. So this 2 GB limit for 32-bit Windows applications is for each individual application. So if you're writing different applications, each of them will have their own 2 GB of memory. Now, if you think you actually need more than 2 GB of memory, putting this option at the beginning of your code would actually give you a little bit more elbow room, and it would compile quite happily. And this would actually give you more memory. So if you ever do actually run out of actual memory on your machine, this would be one approach. But as I said earlier, I have never come across the need to actually use it yet, but who can tell? The other options are more legacy. These meta statements can be used to control the minimum Windows version tag that your program will actually run under. These options allow you to set it to version 3, version 4, or version 5, or even Win95. Now, in the unlikely event that you're actually wanting your program to be able to actually run under these older operating systems, you can actually use this option. But most people these days are running under Windows 10, or at the very least, Windows 8. So setting option version 5 would mean the computer on which your program would run would have to be an absolute minimum of Windows 2000. It would of course run on anything later. The other one that you may want to actually consider using is the stack command. This allows the maximum potential stack size to be set. Now the stack is actually used every time a subroutine is actually called. The operating system actually pushes the location that you came from, the calling routine, onto the stack. And when the subroutine you're actually calling is completed, it then gets that location back off the stack again. The stack has been used to get bigger and smaller depending on how many subroutines we're actually nesting into. Now it will default to a size of 1 MB, which for the majority of programs is usually more than enough. You can use the stack command to increase the potential size of the stack. Again, in most cases, leaving this as the default will suit you fine. But should you need it, the command is actually here. So this has been a short introduction to compile time options. That's it for today. Thank you for watching.